me and thanks for coming. I have presented twice. I think once it was on meta learning. It was in the beginning, and it was before meta learning got like trending. And then I had one presentation about basic stuff. We had data mining stuff in rapid mining, so it was so interesting. But today, I would like to talk a bit more about interesting topic about our company Recombee and recommender systems in machine learning. And my first half of the presentation, and then I will pass word to Radek, who will present the second part, which is more focused on deep learning and stuff like this. Again, in the framework of recommender systems. So, I think most of you already interacted with some recommender systems, for example, in YouTube or whatever service. So, huge companies, they already have their own data science team, and they built their own recommender system, and this is something what is quite important for them, because they found out that it can drive a lot of traffic, and for example, Amazon, they have like 35% of total sales from recommenders and recommendations. So it's quite important, and they know that once they are able to improve the recommender system, then they have better or more profit, and also their customers are quite satisfied because they can find what they are looking for. So you don't, you can find recommender systems in retail, like e-shops, and also in other segments like recommending events and news and so on. And in Recombee, we are providing recommender system as a service. So we are focusing, it's quite nice because you can focus on algorithms and developing the algorithms, and then we outsource, the integration and data collection and stuff like this to our users and clients. So it's quite nice setup. And today I'll talk about the algorithms we are using in Recombee, and I would like to give you some brief overview of different type of methods that are used in the system. We have quite a lot of different businesses in different domains, so our solution is quite universal, and as you see, you can recommend everything. Everywhere, when you have enough users and enough items, you can apply a recommender engine and improve user experience and conversions and so on. So these are the domains where we have most of our customers, mostly in media, like recommending news, videos, and so music and so on. Then in e-commerce, also job boards, travel, or even education. You can recommend some educational materials. So it was just the introduction, and now I will dive into algorithms, because most of you are here because of algorithms, not because of interaction. So there are two types of methods. One is content-based methods, and the second type of methods is so-called collaborative filtering methods. The difference is that the first one is based on attributes of products, and it doesn't take into account behavior and interactions of different users and visitors. So the only thing you can use for the recommendation is the other attributes of products and users. So this type of methods is not able to recommend you something completely different. It just recommends you something which is similar to something you have been interacting in the past. And the second type of method, collaborative filtering, is normally more powerful because it can help you to explore. And here's how it works. So you have multiple users, and you are trying to recommend some movies, for example here, for Alice. And for the recommendations, you use historical data. So this matrix is so-called matrix of ratings, or it can be any interactions. It can be also implicit behavior of clients, but mostly ratings are used. So John gave 5 stars to some movie here, and 1 star to another movie, and so on. So to recommend some movies for Alice, you need to find similar users in the database. So this is something what is very simple, and it's called K-nearest neighbor methods algorithm for recommendation, and it's called user-based K-nearest neighbors, because you are working with users, and you are recommending based on similar users. So in this case, you find out that John is quite similar based on the behavior. He likes similar movies as Alice, so you will recommend movies that that Alice hasn't seen yet. So quite simple. The only trick is that you need to find out the similarity of users, and you can find the similarity by using this interaction matrix. And here is the equation. It's basic cosine similarity. It works well because the matrix is large and it's sparse. So cosine similarity is quite convenient here. Also, correlation, similarity, and other stuff can be used here. Yeah? Another method that can be used to generate recommendations is so-called matrix factorization. Have you heard about it already? No? Maybe half. Okay, so this is something that is not used just in recommender systems, but the recommender system is quite interesting because you have large matrix of ratings. Actually, it should be sparse. Yeah. Here we have a lot of non-empty values, but normally in the recommender system you have very sparse matrix. And just sometimes some interaction, but everything else is empty. Yeah. And then you have two matrices, P and Q. And when you multiply these two smaller matrices, you should get the big one, the rating ones. And when you do the matrix factorization, you somehow compute these two small matrices from the big one. They are small because, okay, here is a small number. It can be like 300, for example. So you can have Milan, and then just 300. So it can be really small. And how to compute it? So when you multiply these two small matrices, you get a small error, reconstruction error on large matrix. You can use a loss. You see that the first part is the reconstruction of error. It's just the multiplication of two small matrices minus the rating matrix. And then the second part is some regularization. Yeah? So you should keep these small matrices with not very high values because you are overfitting them. Yeah? So this is just to prevent overfitting. And this is how the individual rating is computed from two submatrices. And you can use this to compute the error of reconstruction for every non-empty rating in the matrix. Is it clear? Yeah? There are multiple algorithms that can be used. I think most popular is stochastic gradient descent. So you just try to minimize the error by updating these two vectors. So you take one rating here, and then you need to update these two vectors to minimize the error. Yeah? And this is just the learning rate. Okay? So it's one method, and then second most popular method here is called alternating least square method. And here you have one matrix fixed, and you reconstruct the second matrix. Yeah? So for example, P is fixed, and then you compute in one step using general least square method. You compute values in this matrix in order to match the ratings in big matrix. And this is done iteratively. So you fix P, compute Q, and then fix Q, compute P, and change it, alternate this. Yeah? And you need a couple of iterations, like 10, to get convergence here. And again, you receive factorization and something you can work with in the recommender system. So then you can use these small submatrices again and find similarity on these small matrices. Okay? You don't need to pick one. Another approach is based on association rules. So this is something what is not popular because not many people and researchers are able to scale up the association rule algorithms to large data. So these are the rules which were extracted from some movie database. And so each dot here is a movie, and each edge is like fragment interaction. So you have cluster here of rules of some bestseller movie. So when somebody see Spider-Man, you know, everybody saw this, and everybody saw other metrics and other bestsellers. And there are some niches here that are not mainstream, but they are clustered very well, as you see. And how to produce this? You need to use association rule mining algorithm. I must say something about the properties of the rules. You have support of the rule and confidence of the rule. Support is how many times the rule is present in the database. So for example, how many times these two movies were watched together. And then you have confidence, and it's how many times this is valid, and how many times this rule is not valid. So it's confidence, and you can use so-called like minimal support and minimal confidence to extract these rules. So you're using a priori algorithm. So here the a priori algorithm is very simple. You just extract some combinations, and you know that when you have some combinations which are frequent, then you can try to add some other movie. When you have combination which is not frequent, then adding other movie will not help, because it will not be frequent anymore. So you can just like prune this tree and focus on just frequent item sets. And from frequent item sets, you can generate these possible association rules. And from these possible association rules, you can recommend. So when you have some movie in a history, you can recommend other movies. So here you can see some examples how we use it. This is quite nice application we did in data festiak in 2015. It was from card holder data provided by Česká spořitelna, and these items here, dots, are places where you can use your credit card, and these are the transactions, frequent transactions. Yeah? It's a very interesting result because you can explore this graph, and you can, when you zoom, for example, to some small city, you can find out that when somebody buys some food in one shop, then he or she continues in another shop to buy groceries or whatever. Yeah, so you can explore these rules, and you can also use it to recommend new shops, for example, to visit. Yeah. Then I can tell you something also about the plasticity of the algorithms, and there are some regularization of algorithms. So often when you extract just the most frequent rules with the biggest support, you get just bestsellers. Yeah. And once you decrease like minimal support and confidence, you can get into the places which are not bestsellers anymore. They are quite like interesting and long tail. So this is something what we are interested in, and actually you can modify association rules algorithm to prefer not the bestsellers but the long tail items. Another, and promise the last method or group of methods for recommendation is a neural network. Here I show you one typical example of neural network, which is called autoencoder. This neural network has the same number of inputs and outputs, and it tries to like reconstruct the information. This is the bottleneck neurons. So actually, when you, for example, use the interaction matrix, you can do the same trick as when you use factorization using neural network. And you can also use like multiple layers here, so the transformation is not linear but non-linear, so it can be like more advanced. Yeah? So, and here you can see just the simple autoencoder and the loss function of autoencoder you are minimizing. For this, you typically use some Adam algorithm or some normal like gradient descent algorithm. Good. So here's some recap. We are talking about K-nearest neighbor algorithm, which is based on similarities, and this algorithm, the disadvantage is that this algorithm cannot be like normally, for example, association rules, you extract and then in the recall phase, it's pretty quick. Yeah? And here, this is so-called like lazy model. So this is typically computed during the recall. Yeah? So you have to use pre-computed variants of K-nearest neighbor to be able to scale it to big data sets. Then association rules. Again, this algorithm can be modified to work with long tail items and prefer long tail items from bestsellers. Then one variant of matrix factorization, where this is more advanced. It's also taking in account rating of items for individual users. So if one user gives always like high ratings or always low ratings, this algorithm can take into account and make like a relatively contribution. And then one example of deep neural network. So in this case, you train autoencoder to encode attributes. Then you perform matrix factorization on interactions, and you train it together. So this is quite nice because you can somehow put together collaborative filtering and content-based methods into one hybrid algorithm. Another important stuff here is how to evaluate algorithms. It's not easy. Typically, we use the same methodology as in other machine learning approaches. So we have training set and testing set. So we divide historical data just like into two sets, or we can use multiple cross-validation. And we can also divide, the interactions of individual users. So you present some to the algorithm, and then you verify on other interactions which were not seen by the algorithm. So this is typical setup. And mostly people use RMS, error, root mean square, which is pretty simple. And also Netflix price, if you know about it. It was in 2016, very popular. Many, I think at least like 700,000 people like participated. It was really like a large challenge, and they managed to improve this RMSE by 10%. I think this is not the best metric, and we mostly use recall or precision. This is a bit different task. Normally you try to reconstruct rating, but in this case you just work with a list of items that are recommended. And with this list of items, you look how many of them are relevant. And precision is how many are relevant, how much like percentage of relevant from recommended, and recall is percentage of total items. Okay, so you can implement so-called biasing techniques. So you can modify the plasticity of algorithms, and here, for example, you have bestsellers, or somewhere here, and then when you penalize bestsellers, you can increase the diversity of recommendations and get like more diverse recommendation, and at the same time, the precision is increased. And this can work similarly to other algorithms like association rules and so on. So this is what Tomáš, who is not here today, but he's doing it in his dissertation thesis. Here are some examples of algorithms I have mentioned on one database, so you can see that we are able to improve the performance, and like matrix factorization is here, and here is some association rules and so on. And when you run it on different database, it will be different. So everywhere in each scenario, different algorithms are performing well. And what you can do also is ensembling algorithms together, which is even more complicated. So it gets hard. And then another stuff I need to mention is cold start problem, because you don't have interactions every time. Sometimes you have new items or users completely without interactions, or with just one or two interactions. For such users or items, you are not able to use these collaborative filtering approaches. So you need to use these content-based methods. And you can do a lot of like tricks how to improve the algorithms and how to compute the similarity of products, for example, based on their attributes. So, for example, when you have recommendation of articles, you can measure somehow similarity of articles. So when you have Czech articles in media, you need to understand what the article is about, and you need to measure it somehow. Yeah? And it's very difficult. So we are, for example, here using sophisticated natural language processing techniques with our colleagues in China. And here is another example. You have different attributes here, price, categories, some pictures, some description, and you can use this and process this into a vector. And then you measure similarity of these vectors. So this is typical content-based approach. But what you can do here is to compare the similarity, which is based on interactions, here, and the similarity, which is based on attributes, which is here. And somehow try to combine it. And one possible approach here can be to use neural network to combine or to predict interaction similarity from item similarity. So in this case, you can improve the code style significantly. So this is something what is also like state-of-the-art research we are doing in our laboratory. And because it's neural network here, I will pass the word to Radek, who will tell you a bit more about what we are using in this domain.
So thanks. I'm Radek. And I'm gonna talk about deep learning, which is hopefully gonna be a little bit more interesting. And no more equations, I promise. Okay, so there are multiple ways to use deep learning in recommendation because it's a very wide field. So we'll start with something simple, which is predicting ratings. Basically, it's a feed-forward neural network that gets some information, or also called features, of items and users. Let's say one item and one user, and it predicts its rating, meaning it predicts how this user will like this item. I can calculate this for every item in my catalog, then sort these ratings and find out, okay, so this user will like these items the best, so I will recommend these items to him. It's quite simple. And as an example is this paper called Wide and Deep by Google. Why is it interesting? It's because it's not a simple feed-forward network. There would be something like just this part, or this. It's a simple feed-forward network, but this network actually combines the sparse features, which are here, with dense features, which are here, and creates one neural network that calculates only one linear transformation of the sparse features and combines that with the nonlinear transformation. Also, you can say just multiple deep layers of these dense features, combine this information to the rating prediction, and that's what we want, So these features are the features of some item and some user, but they can be anywhere. Doesn't matter. I think it's clear, hopefully. It's like only the beginning. And yeah, another way to look at using deep learning in recommendation is to look at not just a single item and a single user, but to look at a session as a sequence of items as a sequence of actions that somebody has done. You know, like some user has came to our site and they clicked on this thing and then this thing and then this thing. So I have this information that they were doing some sequence of actions, and I try to predict what they will do next and recommend that action to them. So in this case, it's a paper that presents like recurrent neural network, which are used for processing sequences using gated recurrent units. You can also replace them with LSTMs, doesn't matter, whatever, it's just a recurrent neural network that gets a bunch of items, a sequence of items on the input, and outputs, let's say, one item, or basically it outputs a probability distribution over all the items, and you select the item with the highest probability as the item that the user will like the most, you know, in this sequence. And you will recommend that to him. So you're looking at the sequences of items. And this is interesting because you actually incorporate this like time information into this whole problem, meaning you have more information, and you should probably, if you have a good model, be able to use this information and get some better predictive accuracy, let's say. Because in the previous case, you didn't have any time information, you just took a single user and a single item. However, this technique is much more difficult to implement because recurrent neural networks are harder to debug than simple feed-forward networks, so there is always some kind of a trade-off. And yeah. So this is just an interesting project that Andrei Schofer has done. We were not modeling the actual items that the user was interested in, but we were looking at the times where the user was most active, and we were trying to find, okay, so in these times the user was active, what is the next time that the user is going to be active? So you can also do other stuff, like, for example, this with recurrent neural networks and recommendation. And yeah, like the last kind of algorithms that, or let's say ways you can look at deep learning in recommendation is to extract embeddings. Basically, you get usually autoencoder, which is something like this. Pavel already talked about that. And you feed some item into it, it reconstructs this item, but it pushes it through this bottleneck layer, which is lower dimension than the input, and you take this bottleneck layer and call it, okay, so that's my vector representation of the item, in, you know, it has a smaller dimension, it's an embedding. And you can do this with items, you can do this with users, because basically you use it to compress all the information you have about a certain item or a certain user to this one vector that you call an embedding, and you can then use these vectors as an input to all the recommendation algorithms that Pavel has talked about here, and even the deep learning algorithms that I'm talking about here now. And this is the collaborative deep learning that Pavel has been talking about. You can even extend it to, you know, ditch the matrix factorization part and use another autoencoder in place of it, and just have two autoencoders, one encoding items, the other encoding users, and then you take these embeddings and let's say make a dot product of them that approximates some rating. But that's just used for training. You don't actually care about the approximated ratings, you care about the embeddings. And we play with embeddings a lot at Recombee, so I'm gonna show you some examples of image embeddings that we use and what you can do with them, and it's nice to visualize it and look at the power of the embeddings. So you can use, for example, some pre-trained neural network on pre-trained images, and just run your own images through it and get the vector representations, and these are gonna be your embeddings. So, for example, and then you can cluster these embeddings because they're just vectors. So you project them to 2 dimensions with t-SNE, which is t-distributed stochastic neighbor embedding. It's just a projection algorithm to 2 dimensions, and you will get something like this. This is 5,000 images with their embeddings calculated and projected to 2 dimensions. And we're gonna look at some of the clusters here and see what happened. So these are all images from a certain customer that is selling furniture and other like house appliance stuff. So here we see that some like stools are clustered here quite nicely, and then there are some like I don't even know what that is, kind of a chair that looks similar, you know, similar chairs, some stools. Okay, so this is not that surprising. Basically, you know, a table is different than a chair, so it's not gonna put tables and chairs together. So this is what you would expect. So yeah, there are the tables. Okay, not really surprised that it works, because I mean, if I have shown you this 5 years ago, you would probably freak out, but today it's normal. So there are some other interesting clusters. For example, these cups. But you know, they all look the same. They have white background, same shape, but have a completely different letters on them. But it's still, you know, kind of a similar style. So this is more interesting because, you know, U doesn't look at all like E, but it's still together. So yeah, but it's still cups, right? So you think, okay, so maybe just put cups together, but actually there are more cups. But okay, so it kind of works. And then there are some paintings. Again, the paintings have some black outline, some white background and some painting, but they don't have to have white background. They can have dark background. So you can see that it clustered all the paintings together, and then the paintings that were kind of white were together, and then the dark ones were also together. So again, it's kind of nice. And yeah, but I mean, this is a little bit better than you would maybe expect, because it's not just chairs versus tables. They're all paintings, but there are still some differences in them. But we are going to look at something even better. Okay, this is just a close-up of the paintings. You can see that they have some, like, even here, this is kind of interesting, that there are some plants together, but, you know, there is another plant here, so it's not like all the plants are together. Yeah, but we're going to look at a more interesting example. This is a data set with beers. And why is it interesting is because there are only beers, and the beers are either in bottles or in cans. So, of course, there are 2 big clusters of beers and cans. I mean, that's expected. But then, all the bottles have to be, you know, clustered somehow. And you see that these bottles have, you know, similar label, just with different numbers. So that's interesting that the network was able to focus on this part, on the label. It didn't just say, oh, yeah, I mean, it's all bottles, so whatever. But it actually, you know, the information about the label structure is also quite strong in the embedding. And this is actually like really awesome, because if you look at it, these bottles, the labels, they had the same background, the same, you know, font and different numbers, but still all the bottles look really similar. But in this case, like the cans in the question, you can see that they should be together because, you know, you're humans, but they actually have like completely different letters, you know, like the names are different. It has the same font, yeah, sure, but still it's different shapes, different color, like it's red, green, yellow, and the picture is completely different, like some sailor, some whatever this is, mermaid, and also this text is different. So basically everything is different, like the only thing that stayed the same is kind of like this artistic style that is really hard to express, but the network obviously caught up, and it was able to cluster, or let's say the embeddings of these images are quite close, definitely closer than other cans that have different labels. And as you can see here, it's not just that I've selected these, and it happens with other artistic styles of cans. So this is really interesting that it actually works that well, and these are embeddings from pre-trained neural network on completely other images. It just learned to extract these features, these general features of the images, which we can now use to get some information about the image. So now this clustering is just nice to look at. Of course, when you're using the embeddings, you don't project them to 2 dimensions. You use the full embedding, which is like usually 2000 dimensions, 2048, whatever. And you put that as an input to other recommended algorithms. And this is another example of the cans that have different pictures, but similar artistic feel, let's say. It's also quite interesting. This can is completely different from this can, but they're still together. So really nice. And now I'm going to talk about our project that has been done by Ondra Bija. He's somewhere in the audience, so you can talk to him later if you have some complicated questions. And this is the sequence prediction. As I've been talking earlier about the gated recurrent units, the recurrent neural networks, we tried that with LSTMs, like a similar algorithm. So again, what we're trying to do, we have a sequence of purchases. Some user can purchase this, this, and this. I'm asking what's he gonna purchase next, so I can recommend it to him. And probably he could maybe buy it, I don't know, if I get the right kind of item. So how can you approach this? You can start with something simple, not recurrent network, just a simple feed-forward network. So you will feed these, these 3 items, let's say last 3 items in the sequence, and you will feed them to some feed-forward network and get a probability distribution over all the items. And again, select the item with the highest probability, and you're gonna say, okay, so this is the item that's gonna be next in the sequence, right? But if you look at this doesn't take into account the time at all. It's just the 3 items put in as an input. And also you can see here that I've put in the items in one-hot encoding, meaning I didn't use any information about the items. It's basically just IDs. So why am I talking about this? Because I don't have to use just the IDs, I can use the embeddings. So I have some embeddings of the items. For example, I have some pictures for the items, so I can use the embeddings of the pictures instead of the IDs. And this is nice because it has some added information that I can use, and I will hopefully get a better accuracy. So we'll look at how it all works at the end. There's a big table that summarizes the results. So another approach would be to use the LSTMs. It's a recurrent neural network. And basically I just I feed the first purchase, then I feed the second purchase, then I feed the third purchase. This graph is just a recurrent neural network unrolled in time. So yeah, so the recurrent neural network actually looks just like this, and it's getting fed the first purchase, then the second purchase, then the last, then the third, and then you look at the results and say, okay, so this item is going to be next in the sequence. And again, you can do it with one-hot encoded items, or you can use the embeddings. Okay, so we've got our 4 candidates, and we can look at how it actually works and compare it with some baseline. Some simple baseline would be just always recommend bestsellers, like find out what most of the users bought and recommend that, no matter what the user is looking at. So it's a pretty bad model, as you can see. We're looking at some recall at 20. Oh, it's just a measure that don't have time now to explain it, whatever. But the bigger, the better. So here you can see the interaction k nearest neighbors, meaning I'm recommending things that were closest in according to the vectors in the interaction matrix to the items that the user purchased. And here I'm using features, meaning the embeddings. So I'm looking at the closest items and I'm using the embedding vectors. So you see that the embeddings are quite good, but it's similar to this interaction KNN, so 5%. Then I'm gonna look at this simple feed-forward network using one-hot encoding. This is 16% recall, so like 3 times better than the baselines. And if we use images with this like feed-forward network, it didn't actually increase almost at all, which is surprising because you would expect the information in the embeddings to improve the prediction, but in this case it didn't help. I can't really tell you why. Maybe if we tried some other things and played with the architecture a little bit more, maybe you would get different results. It's always you know, a little bit on the water with the neural networks. You can't tell in advance what will happen. So then when we tested the recurrent neural networks, they were, as a whole, they were better than the feed-forward networks because they were using this time information. We were telling it this happened, and then this happened, and then this happened, you know, which these feed-forward nets didn't know. And then when we used images with the recurrent neural networks, it improved even more. So in this case, it was the expected and nice result that we wanted was that, okay, if you use recurrent neural networks and we use the embeddings, we're gonna get the best result. So that's cool. That's what we wanted, and we got like 4 times increase compared to simple baselines, of course. I mean, in reality, we use more complicated algorithms. And this is actually getting to the more complicated algorithms I was talking about now, and that's ensembles, because all the algorithms that I've been talking about and Pavel has been talking about, you can combine them to ensembles. What does that mean? It means you just take all the algorithms that you want to use. They have some outputs, you know, they have some, okay, I think this item is the best for the user, you know, and everyone has different opinions, and you just take their opinions and combine them, and you can combine them by many different ways, by simple voting, or you can combine them with some other model that takes these opinions as an input and outputs another, you know, item that it thinks is best for this user. So this is obviously some complex structure made of these simple models that we were talking about till now. And you can change the structure of this ensemble, as well as, of course, the hyperparameters of all the models, because all the models have some hyperparameters, and this ensemble model has itself some hyperparameters because the structure of these models can be completely different, the weights in the voting can be different, a lot of parameters. So when you have such a large number of parameters, what we're going to do, we need to optimize them somehow. And that's why we developed our own online optimization algorithm that takes these parameters and tries to find some nice configuration of them that performs the best. How to do that is we're gonna use an evolutionary strategy. That means we can come back to this image, and this, what you're looking at, is a fitness landscape, basically a landscape of how I think which area is good. So we have, in this case, we have 2 parameters, k and beta, just 2, so it's nice to visualize, but of course you can optimize multiple parameters. And so you have this space of parameter configurations, and you want to find the best configuration possible for your model. And so you don't know anything, like in this area I haven't explored at all, I don't know anything, like these configurations, maybe they're good, maybe they're bad, I don't know. But here I already explored some areas, so I found out, okay, so parameter configurations here and here were pretty good. Here it was kind of bad, really bad. Right? So I can kind of run this evolutionary strategy as an algorithm that is running on top of this fitness landscape, and it's selecting new points to look at, new points to evaluate, right? So we can look at how it works. These are actual like real-world data on some customer. And so you see that we have already explored something. So this is not the real beginning. We're jumping in the middle of the optimization process. And so these points, these green, blue points are past measurements. The brown points are the latest measurements, and the yellow squares are the new points that we are going to evaluate next. Right? So these yellow points were actually generated by the evolutionary strategy that is running on this space. So what is happening here? You can see that this point was obviously quite bad because it is surrounded by this red abyss. And this point was also quite bad. These points were good. So what I'm going to do next, I'm going to say, okay, so let's look at this area more. Let's exploit a little bit, because of course, you have to balance the exploitation and exploration of the space. You don't want to explore a lot, because then you would be finding all the places that are bad, which is nice that you know that they're bad, but your customer is suffering because you're testing bad configurations. Because what does it mean to test the configuration? You deploy it online and find out how well it is doing. So of course your customer is not going to be happy when you find out that all the configurations you are testing are bad. So you have to be careful. So you're going to be able to find some good place. You want to stay there and maybe explore a little bit, you know. And we evaluate through A/B testing online, meaning these 3 points are going to be evaluated online using A/B testing at the same time. So we can say, okay, so let's say these two, I expect these two to be good, and I don't know anything about this one because it's in an area where I have no idea what's going to be. That's why I explored it. So, yeah. So what happened is that I found out that this point was actually quite bad. These two were good. So now what does it mean? This could be noise, of course, because the real world is really complicated. It's very noisy and a lot of things can happen and you don't really know what's going to happen. That's why you need to test online, because you can't really prepare for the real world. And so I found out, okay, so this point is bad. So let's move in this direction, because this point is good, this point is good. So what I'm gonna do, the new points are here, and one is also here, because I still, you know, kinda don't believe this, but it's still on the edge. I'm not really gonna put a point in the red, because I don't wanna risk a really bad configuration put online. So what happened is that, okay, this point turned out not to be so bad after all, so it was probably noise. This point is really bad, but this point is quite okay. So I found that this area looks good now. This area is also not so bad, so I can, you know, exploit, maybe explore a little bit more here. But I probably won't go here, because as you can see, there are some like red areas here. So maybe I'll have to wait a little bit and to see if the domain changed, or see what happens, and maybe if something radically changes in the world, in my world, which is this space of parameter configurations, I will explore more in some other directions. But right now I'm happy in this place. Okay, so that's how this optimization works. And now we can talk a little bit about reinforcement learning, just for a little while, because it's also reinforcement learning is very wide field, and it has been, you know, very well researched in the past years and many advances in the field. And so basically, modeling a user, it can be thought of as a Markov decision process. which is like the basis of reinforcement learning. So basically you can use almost any reinforcement learning algorithm to model your user, to give the reinforcement learning algorithm the actions that the user has done till now, and ask what is he going to do next. You know, some kind of like a sequence prediction, but with reinforcement learning. And you can use almost any reinforcement learning algorithms. So I just selected like two on the like edges of the whole, let's say, possible choices. This is like bandit algorithms. They are quite simple. For example, this algorithm is based on upper confidence bound. These bandit algorithms are just selecting which action to take, which is like all reinforcement learning algorithms are doing. But they're quite simple. They're not using any deep learning at all. They're fast and easy to implement. On the other hand, you have deep reinforcement learning, which uses deep neural networks to approximate some quality value functions about your states, about your actions. And as an example of what it all means, I've selected this LIRT. It's short for list recommendation using deep reinforcement learning. And what they're doing is that they have a state. Their state is users' past actions. So a sequence of past actions of a user, and they're trying to recommend him a list of items that he will like. So there are two components to the algorithms, actor and critic, which is probably some of you who do reinforcement learning are familiar with these terms, but most of you probably not, so I'll just quickly go through it. It's just that the actor is generating the actions based on the state, and the critic is evaluating this state-action combination and is using a deep neural network to calculate so-called Q value, which means quality of this, let's say, choice. And you can use this to update the actor to make better decisions in the future, like what to do when the user is in this state, what to recommend. There are some pitfalls with the reinforcement learning in offline evaluation, but they also apply for many other algorithms we've mentioned here. That's why we use the online optimization algorithm that I described earlier, because the online world cannot be simply replicated. So we use that very carefully, of course. And so you know that we're not just talking about the algorithms, we're actually using them. We can talk about these two customers and what do they need, their kind of special needs. There is this is Economia, and it's a publishing house, you probably know it. They have websites with articles, news articles. So in this case, you really care about the long-term customer value, because in case of articles, if you recommend some article that is going to be, it can be quite popular. For example, if I have some hospodářské noviny and I recommend some picture of a naked woman on the front page, a lot of people are going to click on it. So if I optimize for the immediate reward, I'm going to be like, yay, that's the best choice I've ever done, I'm going to put naked women everywhere. But that's not the best choice for the long-term value, right? So you need to think about that, and the reinforcement learning algorithms, for example, are inherently very good because they are optimizing for the long-term value by definition. So it's quite good to use them here. On the other hand, there is a company called Showmax, which is a video-on-demand service. They have a lot of shows and a lot of movies. And in this case, of course, you always care about the long-term customer value, but sometimes there are other problems more, at hand. And in this case, to make good recommendations, you would like to use the embeddings that we talked about, but to make embeddings out of movies or out of series is actually much more complicated than to just make embeddings out of pictures, because pictures are easy, but movies are a bunch of pictures. But because two movies consist of similar pictures doesn't mean that these movies are similar, if you understand. So you know, like the users, like the people that watch the movies, they care about the general feel of the movie. They want an action movie, and if like you know, if some movie is from the desert and some other movie is also from the desert, it doesn't mean that they're similar movies. You know, they can be completely different. One can be a romantic comedy, another can be Terminator. I don't know. You know, it's, you don't want to recommend these two movies to the same user just because they're in a desert, right? So in this case, you want to have some sophisticated algorithms to get embeddings out of movies, which is something that we've done in work with Schumach's lab, and they were researching this area of this topic for quite some time. Maybe you've heard a presentation here a couple of weeks ago about how to extract embeddings out of movies, and then we can use these embeddings with all the algorithms that we've just mentioned here. So yeah, if you liked it, you can continue the discussion with us, grab some beer or anything, because there are much more things you can do in recommendation. Something called inverse recommendation. You can recommend users who like that. You know, so the problem is inverse, and also some completely other things that you can do. So yeah, thank you very much. And if you have some questions.
If you have any questions, just please raise your hand and show them, because we have just one microphone, so I will keep this one. Thanks.
Well, my question is also for you a little bit. Is just about like the way you explained, like what if you have can you explain a little bit how those models adjust to? Can you explain a little bit how those models adjust to, like when you are, like, for example, recommending products and there are new products and everything, because based on the whole rule-based thing, and you're not going based on the content, then it's favoring things that people have, interacted with in the past. And so and also the other one was when you were showing for the newspaper, that how does it work for that, because you have new articles coming up.
Yeah, this is actually a very good question. We haven't mentioned that algorithms are perfect, but then you need to make it scalable, and you need to make it adaptive, and you need to make it real time, and you need to process everything in 200 milliseconds and stuff like this. Yeah. So this is something that we haven't been talking about. Also, we have so-called Recombee query language on top of this. And this is like special language which is able to express some business rules. Yeah? For example, recommend me articles that are not older than 22 hours. Yeah? So something like this. Yeah. So you do some pre-filtering and then apply recommendation on some part of the content. Yeah? But still, it will be personalized. Yeah. So this is the stuff. And of course, training new items, some of the algorithms are hard to be online and incremental. Yeah? For example, this matrix factorization is a mess, yeah? Because you have this, you need to run the algorithm, stochastic gradient descent or whatever, yeah? And you have this matrix pre-computed, and then it's hard to change it when you have new product or a new user and so on. So this is something, again, we have been working hard for several years to make this completely happening online, and every time you send some new interaction, it's taken into account immediately, so you get fresh recommendations. But it's really hard, and it's not very scientific. It's more about make this running and in production.
I have a bit technical questions. You talked about the dimensionality reduction through the autoencoder, and you mentioned the autoencoder using images. And I would like to ask if you use this kind of dimensional reduction in other domain, which one? And if you can talk about something about the size of the dimension in the input and output of and about the algorithm, and if you use only binary data on the input, or if you can use also the real numbers, or like that. If you can tell me more about that part of the work of the process.
Yeah, sure. So I don't know, we don't have a board here, right? Never mind. So if you can imagine the autoencoder, it's just like the input dimension can be actually, you were talking about images, they are large, but if you imagine the rating matrix, you have, let's say, 100,000 items. So one user, if you take the row of the user, is 100,000 dimensions. So if I want an embedding of this user, I'm gonna take this vector, I'm gonna put it as an input to the autoencoder. So at the input, it's gonna be 100,000 dimension vector, and I'm gonna, push it through the autoencoder. And in the middle, I can have, for example, 500 dimensions. So yeah, I can use. And your question about the binary data versus the real, of course, in the question of the rating matrix, it's usually ones or zeros. But they don't have to be. I can, for example, get all the information I have about the user, which can be this rating vector. Then I can add some dense vector to it. For example, I have some information about the user, like where he lives, what he likes, how old is he, and stuff like that. So I can take all this information and encode it somehow. It doesn't have to be binary. It can be real numbers, anything I can get as a vector.
So it is not necessary to have binary data for
No.
the input, right?
No, not at all.
And 0, 1.
No. It can be real numbers. Basically. Yeah.
Yes, that is, I think.
Sometimes autoencoder is not like ultimate solution. As you see here,
Sure.
use like multiple methods, and sometimes like EF, IDF, or very like simple text mining approaches are much more convenient and accurate.
How many layers you using if you use autoencoder? 2 only or some more layers?
It depends on the data you're putting at the beginning. So it's anything from 1 to, let's say, even 10, whatever. It depends on the data. You have to experiment with that. You can't really say in advance that, okay, this is a problem that will be solved by 3 layers. It's tough. It doesn't really work that way.
My question about not using one account for many people. Means, as a family, I watch TV, Netflix, or something else. My wife might, and how the algorithm understand who is
Okay.
using now.
So this is like a, I wouldn't say typical problem, but for some services it is. So in that case, you can use the session-based recommendations. I will just say, okay, so in this session you have watched this and this and this. So I will recommend what.
Session time when I watch.
Yeah. No, I mean, for example, if you have watched, like the first episode of Lost in Space and then the second episode, I will recommend you the third one, but I don't need deep learning for that. But yeah, it's a problem. Maybe Pavel has some other insights, but obviously, if you have children watching cartoons and you watching something else, I can cluster it somehow. So there are some techniques. But it's never going to be 100%.
Maybe you could just first classify the session, just based on whatever you have.
Yeah, sure.
To figure out which one.
It's the same as the cluster.
Yeah, this is, I think, typical problem, and especially we have quite a lot of customers providing this IPTV or whatever, yeah, so you never know who is sitting in front of the TV. And most of our clients are trying to solve this by logging, and so the user needs to log in, and then you can be a bit more safe. But of course, there are like technological solutions to cluster sessions, and but I think it will be too expensive for us to make it running in the production. And normally, like our typical situation is these type of customers, they are like using multiple hundreds of thousand recommendations per month. And if you so you need to run some model which is almost the same for everyone. If you have like personalized models, it will require like much more hardware, and the price of the recommendation would be like much more expensive. So in this case, it's also a business issue because they just cannot afford it, because then the subscription needs to be, much higher in order to have, for example, really a model for everyone.
And the next question about botnet and this contract. How are you protecting your system? Because it can be damage your rating, your learning system. And
Yeah, this is also quite interesting stuff. Of course, you can do attacks on recommender system. Mostly we deal with bots, so you can have users which are very suspicious, that are generating just like too many recommendations in given time, so it's just not very probable that it's a real user. So we just don't take such users into account when you learn the system. But of course, when the attacker is very clever, then the behavior can be very sophisticated, and it's very hard, to distinguish such like fake users from the real ones. And it's typical problem of like predictive modeling. So we're trying to predict, but we don't have training data for this. So yeah, it's very hard. So far we use just like simple methods that are eliminating like suspicious users from training.
maybe you have some user store for a user which you know that is a normal user, and this user have a more powerful for this learning system, for a recommendation system, and this new user, I don't know.
Yeah, of course, but sometimes you would be surprised how like powerful anonymous and new users are. So for some of our clients, we have like really hundreds. So most of them, they don't have like very good data. They have some users that are sometimes they are not uploading us everything, and they are not uploading us attributes. So we need to rely just on interactions. And typically, a lot of clients, they improved behavior of the system like 5-fold by uploading interactions of anonymous users. So when they uploaded just paying users, for example, or registered users, the interactions were not as good. So these like anonymous users were able to like exploit and explore new content and make the recommendations much better. So it's you just cannot easily like eliminate it, because you would harm the system.
It was probably partially answered already, but I want to ask how does your solution differ across the domains and across different companies? And for example, do you use the same metric, or is it configurable through this Recombee query language or whatever? Or? Thank you.
So you would be surprised how much similar it's through the domains. So for example, we developed some like special algorithm for one domain, and then we find out that it can be applicable also to another domain. And sometimes we are talking about very advanced algorithms here, but sometimes even like very trivial algorithms such as reminder or other models are very efficient in this combination. And we have, for example, some like periodic models that are modeling the periodicity of users, and this has been developed for some customers in retail, and then we apply this evolutionary algorithm optimization, we apply it in a different domain, and it outperformed the algorithms we expected to work better. So our aim is to have like a large portfolio of algorithms and increasing portfolio of algorithms, and then sophisticated meta-learning system which is able to adapt. Because even one customer can have like a lot of scenarios recommendation. So even for the same like users and items, you can use different algorithms for mailing or homepage or whatever. So for every different scenario, you need to optimize algorithms and optimize these combinations and parameters and stuff like this.
Just shout a question, please.
Okay. So I have a question about your production systems. So since you are using a lot of deep learning models, and your data changes frequently, how do you train these models? Do you train them from scratch, like for example once a week, and use it for the whole week, or do you fine tune it, or what is your how do you update these systems? And do you if you do some kind of transfer learning, do you do it across the domains? For example, like can you take these embeddings from one client and use it for another one? And if yes, then follow-up question to that is how do you deal with GDPR in this case?
It's a pretty difficult question. We have like dream recommender system which is like far away and it's ultimate, and it's just you have new user coming and everything sets up automatically, and we collect these meta features and everything is optimized and whatever. But we are far from that. So, for example, for these deep learning algorithms, we don't have like fully automated system to make it online. So we learn it once a time. But because we use like Ensembles, the other algorithms that are capable of updating more frequently are winning and making like diversity in the recommendation in the better sense. And as you said, like GDPR maybe, it's a good question, because we have a lot of clients now asking us about GDPR and so maybe everybody has. We don't use the data from like different databases and transfer learning between databases. This is not our approach. So we work just on the data client provided, and we typically use anonymous users. So like most of the stuff needs to be done by our customers, and we are just using anonymous sessions and anonymous users to make personalized recommendations. So this is quite easy. And of course we need to provide all the security stuff and stuff like this. We have chief data security officer over there, so you can ask him.
And did you find that it's better to train the models from scratch, or just to fine-tune them, or something like this?
It depends, of course. So yeah, I mean, some of the models you need to train them from scratch, of course, because that's what they do. Like if you want to capture some of the like structure in your data, then you need to train that from scratch. But if you want some other models just getting embeddings, then you can fine-tune them, of course, like especially with the pictures and stuff like that, you can use pre-trained models. So yeah, it depends on the use case and on the model you use.
And we are using, you don't see now, but there were slides about these combinations of algorithms, like we call it template because it's kind of like similar. And you can use like templates which are very like powerful in some domains, and you can reuse it in like similar scenarios. Yeah? So when you have a new customer and you identify the scenario, you can just start with some template that is appropriate for this scenario. Actually, we are introducing some new parameters to API, which will be where you will be able also to configure it somehow. But our like ultimate approach is to make it completely by using our artificial intelligence.
So my question is, how is it different in the real world compared to offline validation? So you mentioned that it is different, but I'm just asking how much, maybe based on the metrics that you mentioned in the beginning.
How is what different?
So you get like twice as big error rate, or like?
I think I can answer this. Yeah. So surprisingly different. We are also academicians a little bit, and we are writing some papers sometimes, and in the scientific community we have like few data sets, and you evaluate offline performance, and that's it. And then if you increase the offline performance by 2%, your publication is accepted, well done. But the real world is completely different, and sometimes that's why we are doing also this online optimization, and we are trying to find the best technique how to evaluate algorithms in offline, because of course you don't want to set up some algorithm to a customer which is not perfect and which is evolving from some suboptimal state. Yeah. So here the most promising, I think, is the reinforcement learning, but it's pretty difficult, and I think you need to invite us one more time for the reinforcement learning talk, and so because it's about when you have offline data, there was typically some recommendation strategy used in the past, and then you evaluate like new recommendation strategy on this offline data, and sometimes the overlap doesn't necessarily need to be too big, so you need to deal with this, and this is something what we are solving with this reinforcement learning.
You haven't talked about experimental design much, so I was wondering how do you address, let's say, attribution part of the problem? How do you know that the interaction is driven by a recommendation engine when compared to, let's say, something other? Because on a website there is a lot of things going on there, and how do you attribute the interaction to the recommendation engine itself?
As I said, we outsource a lot of things to our customers. Yeah. So this is one of these.
Okay.